Hello everyone, this is Manjunath. In today's class, I'll be explaining you the memory organization in 8051 microcontrollers. On the screen you see the memory arrangement for program memory. So we have a signal in 8051 called as external address bar or EA bar. So if it is tied to VCC, the reset vector starts in the internal program memory of 8051. So if it is a 4K, the internal memory address from 0 to 4K will be accessed to the internal memory, and from address 4K to 64K will be addressed to the external program memory. So from 0 to 4K there won't be any address signals generated on the port 0 and port 2 pins. Okay, so it accesses the internal memory itself for instruction code and the data. If you want to use full address space from 0 to FFFX as part of the external program memory, then you have to tie this EA bar to ground. So in case if you have a ROM-less chip, say for example 8031, so you need to tie EA bar to ground, and you will have the full 64K address lines generated to access the external device. And also one more catch is here, suppose you have a flash based microcontrollers or ROM based microcontrollers with internal memory, and over the age or due to some reason the internal program memory is gone bad and your controller is still good to execute instructions, you can still use them with the external program memory by tying this EA bar to ground and interfacing the external RAM and ROM or the flash memory, and use this microcontroller as a processor. So it literally acts as a 8031 controller. So let's look into the internal memory organization. So here we have internal memory organization for both the 8051 and 8052 architectures. The only difference with 8052 architecture is that it has additional 128 bytes of internal RAM, which is placed in the upper half of the internal RAM address space, that is from 80 FFX. Okay. So let's see. At the lower address from 0 to 7 we have a register bank 0, and 8 to F we have register bank 1, and from hexadecimal 10 to 17 we have register bank 2, and from 18 to 1F we have register bank 3. So 8051 has 8 registers from R0 to R7. So addressing those registers will be mapped to one of these 4 banks based on the configuration values or the bank selection bits in the program status word. So this is very useful feature in 8051. Suppose you have a main loop code using the register banks from bank 0, and you have an interrupt service routine using the register bank 1. You don't have to save all the registers by pushing them into the stack. Instead, you can simply switch the bank at the beginning of the interrupt service routine to bank 1, and rest of the code uses the register access, uses the registers from R0 to R7 for the register access. So this way it speeds up. The context switching really speeds up. So see, another feature is that suppose you are using 2 or 3 functions, and say the caller is using all 7 registers, and the called function or the callee is also using the registers, and every time we call we may have to back up the registers. If such a requirement is there, in that case we can configure, or we can write code in such a way that for the caller function to use register bank 0 and the called function or the callee to use register bank 1. So all you need to do is, just before executing the code within the function, you need to configure those bank selection bits to use the respective register bank. Okay, on top of the register banks we have a 16 bytes bit addressable area, that is from address 20x to 22fx, and on the bottom right you have the expanded view of that. So the lower address, that is 20, its least significant bit is addressed as 0 and its most significant bit is addressed as 7. Then the next byte, that is at address 21, its least significant bit is addressed as 8 and its most significant as F, and it goes on until 2F, whose most significant bit is addressed as 7F. So totally we have 128 bits that are addressable in the bit addressable mode. So most of your bit addressable or bit operation or bit manipulation instructions can use these addresses to access the respective bit. Okay. On top of the bit addressable region, that is from 30 to 7F, is the RAM area, so which is available for your global variables, and after global variables it is available for the stack region. So you have to configure the stack pointer to point to the unused region of the scratchpad area after all the global variables are used. Even these register banks also, it's optional to use. If your code demands or does not demand to have all 4 banks, you can simply use 1 or 2 banks as required, and the remaining locations can be used as a scratchpad region. Even this bit addressable area also, if your program does not demand for a bit addressable RAM or the bit RAMs, in that case even this can be used as a scratchpad RAM. So you can configure stack to be pointing anywhere between 8 to address 8 to 7F. Okay. Then above 7F, that is from upper half of this address space, that is from 80 to FF, in direct addressing mode, like for example instruction move 90x, 55, so which is actually moving an immediate value 55 to address 90x. So in 90x you have some special function registers. So direct addressing mode will actually access a special function register, and indirect addressing mode will actually access the upper half of the RAM. So instructions like move at R0, A, if R0 value in R0 is between 80 and FF, it actually access this physical area, upper RAM area, not the SFR area. So these two upper half of the internal address space is actually overlapped. So if you make direct access, it will actually physically access the SFR registers, and if you do indirect access, it will physically access the upper RAM region. Okay, so this is like a overlapping technique used in 8051. Yeah, that is all for today's class. If you like this video, please subscribe and like. I'll come up with more videos on explaining about each and every peripherals of 8051 and how to use them and how to configure them. And also I'll come up with a video to explain you about instruction set and addressing modes. Until then, goodbye and see you.